My name is Ki-young Lee from Seoul National University, and thanks to Dean Chen for giving me the easiest job as a chair. The next speaker will be Professor Joel SCHWARTZ, and I'm going to make it just like one announcement that he is a professor of environmental epidemiology at Harvard T.H. Chan School of Public Health. And also he's a director of Harvard Center for Risk Assessment. And please welcome Professor SCHWARTZ.
Okay, well, thank you very much, and thank you for inviting me to be here. I'm really enjoying it. I'd like to talk to you a little bit about health and the climate. And I want to talk about a narrow segment of that. So I'm not going to talk about vector-borne disease. I'm not going to talk about many of the other things that, like drowning, that can happen as a result of climate change. I am going to focus fairly narrowly on what do we know about the effects of temperature on human health, and how can we do a better job, not just in learning about them, but in improving public health by doing things a little better, okay? So with that, what do we know about the direct effects of temperature? Well, if you ask most people that, they'll say, well, gee, you know, if it gets really hot, more people die. And that's true. And they might think a little bit and say, yeah, and if it gets very cold, more people die. And that's also true. Both of those are true, and they're relatively unimportant to the health effects of temperature on human health. And they're relatively unimportant. Well, I'll get to why that's the case, okay? But the fact is, and I'll try to show you this, that more people die not just when it's really hot, but when it's somewhat hot. And not just when it's really cold, but when it's somewhat cold. And those days occur a lot more frequently. So it's just like the radon story, you know. EPA has a level of 4 for an acceptable amount of radon in the basement. If you do a quantitative risk assessment, the number of radon-related lung cancers in homes that are below that level is considerably larger than in the homes that exceed that level. Not because the risk isn't lower in those less exposed homes, but because there are a lot more of them. And so the risk of moderately hot temperature is a lot lower than the risk of extremely hot days, but there are a lot more days. And so I will talk about that and what we might want to draw in terms of public health policies about it. But first, let me address the question of confounding. Confounding is something that we have to worry about in any study. And the major factor that confounds studies of the acute effects of temperature on human health is seasonality, because temperature varies seasonally, but it's not the only thing that varies seasonally. And so the first question we want to ask when we start thinking about these less extreme temperatures is that really true, or could we just not be dealing with other things happening with season. Well, these are, pardon me, two dose response curves between temperature and daily deaths in New York City. And the black one, so here, well, it does the right thing. More people die when it's hot, more people die when it's cold. And that's what you get if you don't control for season. If you do control for season, it looks a fair amount different. So the two major differences are the deaths start increasing at much lower temperatures after you control for season as temperatures get warmer. And the effect of cold temperature is dramatically lower and only occurs at pretty cold temperatures. And at moderately cold temperatures, it's gone. Now that's in New York. One of the other things that we've learned, of course, is that temperature is not like air pollution. The dose-response relationships don't look the same everywhere. Now, one thing you might say to me is, okay, these curves are different. How do I know which one is right? You know, you controlled for season. Well, but maybe season is temperature. And, you know, the black curve is the one that you ought to use. So how can I figure that out? Well, you know, back in Epidemiology 101, you know, if I was worried that something was confounded by cigarette smoking, one of the things I might do is I might say, well, let me do the analysis separately in smokers and non-smokers, and if I still see the association with my exposure in both of them, then, you know, it's not confounded. That's what's going on. So what we decided to do is to do a stratified analysis by month. Now, the problem with doing a stratified analysis by month is there are roughly 30 days in a month, and that's not a lot of observations. But there are many years. So what we did is we put together data from 1962 onward. So we had a lot of Januaries, a lot of Februaries, a lot of Marches. And so we had many days in each month, and we looked at the dose-response relationship with temperature by month. Okay? And that also allowed us to ask a second question, which is we put up these dose-response curves, right? So what this dose-response curve says is that this is what happens. This is the percent difference from mean mortality in New York at 30 degrees. If I believe this curve, or if I believe that curve, it's higher, right? But that assumes that it doesn't matter when that 30-degree day happened. There's one answer in each of these curves for every temperature. Maybe that's not true. Maybe it does matter when that 30-degree day happens. So if I analyze every month separately, I can look at that question. Does 30 degrees matter the same amount at different times of the year? So this is looking at 50 odd years of data in New York City, fitting a separate dose response for each month. Now, if I look at 30 degrees now, okay, yellow is July. Okay, 30 degrees in July, the percent difference from the mean deaths in that month is 0. 30 degrees in New York in July, that's a pretty standard temperature in July. These are 24-hour, I should mention. But these little X's, right, that's April. 30 degrees in April, and you're looking at an 18% increase in the number of deaths. So no, there isn't one dose-response relationship with a given response at a given temperature. There's a different response at that temperature earlier in the year than there is in the middle of the summer. And if I look at like October, which is these circles with plus signs in the middle, it's not quite as high as April, but it's certainly significantly different than July. So as you start moving into the fall, and 30-degree days aren't very common, when you get one, more people die. On the other hand, if I sort of, with my eye, smooth together these curves here, what it looks like is that things start going up in terms of mortality, more like somewhere between 10 and 20 degrees on average, and not much is happening at cold temperatures, which looks a lot like that red curve. So that red curve is pretty good on average, and so really we did have confounding. And not controlling well enough for season results in an overestimate of cold-related deaths in New York. Okay. But the other important factor is that when a temperature occurs, has a big impact on the health response. Now, why, you might ask, is there more confounding for cold than for heat by season? So there are 4 figures here, and let me go over them. This is a plot of temperature versus day between 1992 and 2001 in Detroit. And you can see the temperature is very seasonal. Yes, there's sort of fluctuations within this curve, but most of the variation actually is seasonal, right? And Detroit has a continental climate. It gets, again, these are 24-hour temperatures, so 30 degrees means a max of about 35. It's getting pretty hot in the summer, and -10 means a min of about -15. It's getting pretty cold in the winter in Detroit. And this is the plot over the same time period of temperatures in Honolulu. And in the pits of the winter, it can get down to 20 degrees. Now, it's really hard to die of the cold in 20 degrees. Over here, what you see is a plot of the percent difference from the mean mortality rate over time in Detroit and in Michigan, and you can see it goes up and down seasonally. More people die in the winter And here's the same plot in Honolulu. And it goes up and down, and more people die in the winter, and the percent swing between winter and summer in mortality rates is about the same in Honolulu as it is in Detroit. So that tells me there are other things going on for sure that increase the mortality rate in the northern hemisphere in the winter that have nothing to do with cold-related deaths. And therefore, we do need to control for it. So I think we can conclude that that red curve really did look like the right one, but the even better one was the one where you had different lines for every month. So we took a bunch of US cities and we clustered them by what their weather patterns were. And so this is one of those clusters. It has about 30 cities in sort of a tier that goes westward across the US from New York into the Midwest. And we then fit these curves in these cities that have roughly the same temperature patterns, right? And so we could meta-analyze those lines and get even more power. And when we did that, what you see is, again, here's the curve in April. So here at 25 degrees, there's a really big difference between what's happening in April versus what's happening in July. And April, May, June, July, August, September, we're back up here. So there's clearly adaptation to the prevailing temperature in that month, in that city, going on, and as a result of which, people don't respond the same at the same temperature at different times of the year. So why am I belaboring this? Because our public health response to temperature is to call alerts when it gets really, really hot, which is in July and August. And in April, we never call an alert. And in May, we never call because we look it up and we say, well, it's not that hot. Well, it may not be that hot for July, but it's really hot for April, and more people are dying as a result of that. And maybe we need to start modifying our public health response to take that into account and to say we need month-specific thresholds for when we're going to call a heat warning and tell people they need to start taking precautions, stay in air conditioning, drink plenty of fluids, do various other things that will help protect yourself. So we've actually known this for, more than a year or two, but we haven't translated it into public policy. And so I think there's an opportunity for us to do a better job of, as Ruth said, getting the policymakers to see what the implications of our studies are. So this is one of those dose-response curves in Paris. So this is the 2993? I don't think so. 1993, 2003 heat wave. I don't know how that happened. The 2003 heat wave, and mortality rates really skyrocketed then in Paris. Okay? And that's very impressive. You look at that, you go, wow. Okay? Now, what you see down here is something that's called a rug plot. So it's like one of those nice, Ryer rugs. You got these tufts coming up, and there's one line for each day. So this is 37 years of days. That's a lot of days, right? But out here, you can see the individual days that were getting that hot. So yes, there were a lot of deaths in that heat wave. You can't see the individual days between 30 and 35 because there are so many of them. And so this is a log relative risk, log rate ratio here. So when you're looking at there, you know, you're maybe at a 10% increase in daily deaths. A 10% increase in daily deaths for that many days is killing a lot more people than the 2003 or 2993 heat wave, which I hear is going to be really bad. And so, again, we're putting too much emphasis on extreme days, and we need to start paying attention to what's happening at days that aren't quite so extreme, but happen a lot more often. So that's another lesson I think we have in terms of trying to translate, and people have been publishing curves like this for decades, right? I mean, it's not like we haven't seen this. We all know this if you're in the field and doing these studies, but people have heat wave warnings, and that's it. Now, of course, I don't want to have a warning every day in July, right? Because then people will stop paying attention. So there may be need for different kinds of approaches to deal with this problem. Like, you know, New York City planted 1 million trees in 6 years. 1 million trees. And they're not that big, you know, they didn't plant 10-meter trees, but they'll grow and they're going to produce a lot of shade, right? Maybe that's what we need to do, or maybe there's something else we need to do, but we need to start thinking about what are the policies that will address this problem that we've identified. So this is part of the MCC consortium. This was a study that asked the question that I think is related to here, right? I mean, what is this saying? It's saying that there's some acclimatization that happens so that by the time it gets to being July, 25 degrees is no big deal, right? Because you're used to it being that warm. Well, whoops, wrong button. Well, that's okay, looking month by month. What happens if the temperature is more variable? Does that impede your ability to adapt? So what this study looked at was controlling for the effect of daily mean temperature. What additional effect do you see if there was a lot of variability in temperature in the preceding days, which might have made it harder to adapt? Looking at the preceding 2 days up to the preceding 7 days. And in most of these countries, what you see is that there is additional mortality if the preceding days were more variable. And, you know, the longer averaging periods seem to be more important. Thailand looks different, but by and large, increased variability seems to impede the adaptation that we saw made July less dangerous than April at the same temperature. So even shorter than a month seems to matter for those things. Now, the bad news is that it's not just the case that temperatures are going up. So this is looking at 20 years of data at weather stations in, North America and doing a little bit of smoothing. And what we see is that in June, July, and August, there's this swath from sort of the upper tier of the US heading down to the southeast, where the standard deviation of temperature has dropped by 1 degree. That's a big change for standard deviations. And in Mexico, the entire country has seen a substantial drop in the standard deviation of temperature. So we're seeing changes in the standard deviation of temperature. We're seeing them in summer. We're also seeing them in winter, where, went up, not down. Sorry, red is up. I'm not colorblind, just stupid. So it went up. So there's more standard deviation going on in much of the US and all of Mexico. Standard deviation going up impedes adaptation to the temperature. That's bad. In winter, the standard deviation is going down in the northern part of the US, and then we have mixed things happening for the transitional seasons. Well, sorry about this, but the power supply for my laptop stopped working, so I had to finish making my slides on my iPad, and it. Now, another thing I think we can learn is that there have been many publications where people have said, okay, in 2050, here's how many more people will die in heat waves, or things of that ilk, right? We look at projections for changes in temperature, and then we take that and we extrapolate the dose response curves we have, and we say that's what will happen. And no one pays any attention to those papers, at least no policymakers that I've seen, right? And they have a point, right? I mean, first of all, how do I know what the temperature is going to be in 2050, right? Well, we run these generalized circulation models, and, they all give different answers, right? So then we average 20 of them. That's what I do. Other people do it too. You take CMIP 5, you average 20 of them and say, well, that maybe that's closer to the truth, and it probably is, but policymakers could really say, yeah, but, I mean, how good is it? And I could tell them, just like I have to wait for the third generation of my study participants before I can tell you what's going on. I said, check back with me in 2050, and I'll tell you how good the models are, right? And then we take these dose response curves, right? And we say, well, let's assume that they'll be the same in 2050. And people say, well, how sure are you about that? And I say, well, check back with me in 2050, and I'll let you know. And I do this risk assessment. And they don't pay attention. And what we're missing is climate change is not just about the future. The climate has already changed. And I may not know what the temperature will be in Taipei in 2050, but I'm pretty sure I know what it was in 2010. And it was probably hotter than it was in 1990. So we can go backwards. Not only that, I can take the mortality data and see what the dose response curve was in 2010. I don't have to try to figure out what will happen. And so climate change has actually happened. We can do risk assessments and say, this is what climate change has already done to heat-related deaths. And I'm as guilty as any, we don't do that, but it's already happened. So, and here again, this isn't a climate model. These are NOAA weather stations. So these are the United States as a whole, southeast, southwest, south central, northeast, intermountain, that's like the Rocky Mountains, etc. Different regions of the country. And this is what has happened to temperature per year in those different regions in the cold and warm season. Okay, and they've been going up. We can ask, what has that done? Here's another piece of bad news. Wind speed has been going down. Wind speed is really nice to have in the summer, and we're getting less of it. And so that is an underappreciated part of climate change, which is going to affect health, I believe. And one of the ways, it will affect health is through air pollution. Because the other thing we can say is, not only has it gotten hotter already, but that as a result of that, we have more secondary pollutants than we would have had otherwise, which means ozone and secondary organic aerosols, particles. Okay? And we can calculate that. We can estimate that. And so if we have hotter days and lower wind speed, so the air has more time to cook in those hotter days before it heads off to the Atlantic Ocean, we're going to get more exposure. And so we took a look at what that was, and so this is a busy graph. So this is showing the change in ozone concentrations that occurred over time, because we measure it. We know how much ozone has changed, right? And then we estimated what would have happened had the temperature not gone up, and the difference is the temperature-related penalty. And so what you can see, and that's this black bar, in each of the regions of the United States, and then nationally, there is more ozone than we would have had it not gotten warmer in the cold season. And in the warm season, of course, these bars are much higher. And, particularly in the southeastern U.S., we're seeing, 0.6 ppb per year more ozone than we would have had, right? It was going down because of pollution controls, but it would have gone down a lot more than twice as fast in the southeast, for example, had the temperature not gone up. And here's the penalty for particles, not as impressive. Again, the southeast tends to be the one that's most affected, although in this case, the northeast is also showing a penalty. And so we are paying a price, not in the future, not based on trying to run CMAQ for 2020, guessing what the emissions would be. But by going back in time, we can say how many more people died in the last 20 years as a result of the climate-related penalty on the formation of secondary pollutants, and the answer was 20,000. That's a fair amount. And so I am now out of time, so I will, well, one last thing, just to abuse my hosts. We do all these studies by taking one temperature monitor in a city and saying, okay, and what happens? But there isn't one temperature in a city. So this is Boston, one of my favorite cities, right? And this is the annual average temperature predicted from a model we fit, and where we estimated the temperature every day in every square kilometer of the area using satellite measurements at night of surface radiance and calibrating that to multiple real temperature measurements. And then we could estimate what's going on, and you can see there's a lot of variation in there. I can do it, other people can do it. Someone has, using a slightly different methodology, a 1 kilometer grid temperature map for the entire North America. We need to start using these in our studies. So that's another lesson we can take from things that already exist that could be used better, in this case by us and not the policymakers. And with that, I will be quiet. Right.
For talk, as we can feel, air conditioner is everywhere in Taiwan here, but the heater is everywhere in New York or Boston. So if we do the same analysis, how would you think maybe there will be slightly different outcome? But I think trees are still necessary.
This gives me an excuse to go back to this picture. Thank you very much. So this is the dose response curve doing meta-analyses of the cities in different countries. And it illustrates two things. One is, and these are not in degrees, this is in percentiles of temperature. And what you can see is the curves don't look the same everywhere. So yeah, in the US, everybody has heating. We don't see a lot going on in the winter, but in Japan, we do. And in South Korea, we do. In Spain, well, they don't have winter in Spain, so it, but cold temperature that, doesn't mean much there. But, the dose response curves are different everywhere depending on what kind of weather you have. So you need to do it locally to figure out what's going on. The other thing that you see here is this green curve is the curve from 1993, and the blue one is from 2000. And the effect of heat, well, not in Australia, and not in the UK, but in Japan and Spain and the US and Canada, in many places, the effect of heat has gone down, which is another reason why it's really hard to say what's going to happen in 2050. But I can show policymakers that more people died because it got hotter in the past 20 years, and maybe they'll listen.
Okay, thank you. With that, please give him a hand for the very nice lecture. Thank you.